Okay, let's get started. So welcome. My name is Stephen Kelly. I'm going to talk to you about embracing modern CMake. It's always a nice thing to have so many people in one room who all have very positive feelings about CMake. So who has positive feelings about CMake? Put up your hand. I'm actually surprised how many. Yeah, a lot of people don't like CMake. CMake has been around for a long time. It has a lot of cruft, and you do hit into it, and you do see it in code that other people have written. So I want to tell you about Modern CMake, what that is, where it came from, and how you can recognize the difference. So a little bit about my background. I've been writing C++ code in open source for about 10 years, starting out in KDE with Kmail and KDE Pim, getting into the libraries, and then therefore getting into Qt and into CMake. So I wrote the CMake integration that shipped with Qt 5, and I thought, well, CMake isn't good enough, so I started working on CMake then as well. More recently, I've been working a bit on Clang and Clang Tidy, just to help you refactor your code a little bit better and more mechanically. So that's kind of how I got from doing KDE work to doing CMake work and creating Modern CMake. So CMake is a build system generator. That's, it's not so much related to make in that make invokes your compiler, but CMake generates other stuff, which then in turn invokes your compiler. It stands for cross-platform make because that was what was relevant back in 2000 when it was created. Different make systems existed, but these days CMake also generates your build files for Ninja and for Visual Studio and for Xcode, and actually for some other systems too. It's part of a larger suite of productivity and test tools such as CTest and CPack. I'm not going to be talking about those, but they integrate very well with CMake if you're using CMake already. Here's just a plot of CMake contributors over the last 2 years. I just kind of like to show this kind of thing to show where CMake is coming from. Along the bottom, you see Brad King. He's the maintainer of CMake. He reviews everything, does a great job. And above that, you see all these contributions from all the other people. But this is the last 2 years. I'm actually going to go back to about 4 years ago when this is me creating Modern CMake. So I want to just show this because it shows you how old Modern CMake actually is. So it's so old that even your Ubuntu 16.04 system already has a modern enough CMake to do everything that I'm going to show in this presentation. So just to sort of set the scene a little bit, when I'm talking about a build system, I'm talking about the stuff that you're building from source, and I have a dotted line around that. And that can include various libraries that you're building and executables, and there could be dependencies between them. And outside of that dotted box, there's other stuff. So your external dependencies. It could be Qt, Boost, Google, Protobuf, anything. But what I'm going to mostly be talking about is the stuff inside of this box. So you're creating some libraries and some executables, and those things depend on each other. Where CMake shines is in finding dependencies. There's a lot of cross-platform, reliable ways to find external dependencies, such as Qt and Boost. It also excels in portability in that you can use it with various build system generators, as I already mentioned, Visual Studio and Make. Code generation, you can define custom commands and custom targets, for example, to generate your mock code in a Qt program. There's also multi-language support. This keeps growing. I think we've got C# and Swift support in CMake now as well. So if you have a multilingual build system, CMake can now handle that too. So Modern CMake it's kind of a mindset. It's a little bit philosophical in that sense. And what it aims to do is get you writing less code, less CMake code, have that code be more clean and dry, don't repeat yourself, and have your CMake code be more target focused. And that, this sort of, if you get this right, the other stuff just follows from that. If you get your code target focused, it'll automatically be more clean and you'll have less of it. So I mentioned this already, but the good news is that everything I'm showing you, you can already use. So I think everything in this presentation is present in CMake 3.1, released in December 2014, and present on Travis for a long time, Debbie and Jesse, and at least Ubuntu 16.04. I'm going to show you some other stuff that was introduced in 2.8.11 already. So even if you're still depending on 12.04, there's some things in this presentation that you'll still be able to use. So a hello world, well, maybe a few steps above hello world CMake build system might look like this. What we have is we're defining the minimum version that we depend on, a project name, define a library called libsalutation, which consists of salutation.cpp. We then also have an executable called hello, which is built from hello.cpp. And we say that hello links to libsalutation. So you can just kind of imagine that hello.cpp is somehow going to use the functionality from libsalutation. And just to add a little bit more interestingness and complexity, goodbye.cpp is built into goodbye executable, and that also depends on libsalutation. So this isn't too complicated. We're just defining 3 different targets, and 2 of them depend on the library. And this is not a bad start. But let's look closer at this line number 1, because it's often overlooked and people don't really know what it means, I think. So let's talk about policies. When we have a CMake minimum required line, it specifies a version, and that has a couple of meanings. That'll cause your CMake executable to fail at runtime if your version is lower than version 2.8. It'll also populate a variable, so you can test in your CMake code what the minimum required version is. You might want to do that if you're going to guard the use of newer features if they're available, for example. It also resets runtime behavior of CMake with policies. And this is what I want to talk about, essentially. What are policies? So policies are a system built into CMake for deprecating old behavior. Often if we hit a bug in CMake, we'll create a policy so that we maintain the buggy behavior, but we also have new behavior which is more sane. And we'll give you a warning if you're accidentally depending on the old behavior. That might mean something like the link order is incorrect on your command line that we generate. And so we'd have a policy for, generating the correct link order. So all policies are in the warn state by default, and you can set them individually. Every time that you have a CMake minimum required line, that is associated with a newest policy. So if I say that my CMake minimum is 3.3, policy 57 and below will all be set to new behavior instead of the old behavior. And similarly, if I say the minimum required is 3.2, policy 55 and below will be set to new behavior, and all the others will be old behavior. And everything newer will be warn. So here's how you would set a policy individually. You use the CMake policy command, and you would set it to new if it's available. So you can test whether a policy is available. Policy 53 is a policy which changed how CMake parses your CMake file. It changed how variables are processed. It actually created a large speed improvement in how variables are processed, but because it had a slight behavior change, we had to create a policy for it. And it was introduced after 3.0, so if my minimum is 3.0, it's worn by default, so I set it explicitly to new. It is possible to set a policy to old. You almost never want to do that. If you're setting a policy to old, that is a good indication that you are not using Modern CMake. So when you would set a policy to old, here's a few conditions that you'd want to satisfy before doing that. You might want to do it if you're close to your own release, but a new CMake version has just been released, and that's warning on your code. And you don't want to have those warnings when your clients are building your code, so you would set the policy to old in that case. But even if you do want to have a plan to migrate to the new behavior of the policy. And one of the reasons for that, kind of, it reaches C++ developers sometimes if you can put things in terms of performance. Any policy which exists will have a cost of implementing the old behavior, and there will be a cost of implementing the new behavior. So say in the case of policy 53, the old slow way of parsing variables and the new faster way. But by default, if that thing is worn setting, it'll actually do both, and it'll compare the output. So there'll be extra overhead in order to give you the warning. So you want to always make sure that you set policies to new if your build system can handle it. But just in terms of how that code would look, you would just use CMake policy to set the policy to old. And you would do that even though the version is much newer. So you use a new version to get new features, but then you set the policy to old to get old behavior in that specific case. But usually what you would do is you would have a list of policies that you get warnings about, but which actually you want the new behavior for. And you set up a loop, and you'd say if the policy exists, set it to new. And you would be able to remove this code once your version is so high that those policies are already set to new. So you'll see this in a lot of modern CMake code. There are some policies which don't warn you by default. Here's the list of them. They don't warn by default because there would be too many warnings. But you can just know that they exist, and if you get strange behavior, you can try to enable them and see if that helps. So what I'm trying to do in this talk is just give you a list of guidelines that you can take back to your office on Monday and use them to implement Modern CMake. So the first one is use up-to-date policy settings in your code. I see a lot of code online on GitHub, etc., where they say CMake minimum version 2.8, and that means 2.8.0, which was released about 10 years ago. And every policy since then is set to warn. So you don't want to be doing that. Make sure you use a more recent version of CMake. All right, so the first thing that I want to talk to you about regarding Modern CMake is usage requirements. That's the idea that a target that you create, such as a library, knows what include directories you have to use in order to use that library. So for example, if you're using Qt, the Qt libraries know that you need to add -i blah 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 Qt core to your command line in order to be able to process pound include QString. So the Qt core library knows that, and it needs to communicate that to all users of Qt core. So that concept is what we call a usage requirement. So we've seen this slide already. It's exactly the same as before. I'm defining a library and two executables. And what we might want to do instead is put those things into directories. So I've put the libraries into the libraries directory and the executables into the executable directory. And now the question is, how can we make it still work? So obviously, if hello.cpp pend includes salutation.h, that will work because those two are in the same directory here. Once I've moved them to new directories, there's going to have to be a -i added to the compile line. So how do we express that? Well, the old way is to use the include directories command with some variable that gets defined somewhere. Here it's called salutation includes. This is the old way because it's using the include directories command and because it's using a variable. I'm going to talk in more depth about both of those issues. But a third downside of this is that it's very wordy. We should have a way of writing our CMake code such that we just don't need that line at all. So another way that we could write this is we could use the target include directories command instead of the include directories command. That's a little bit better because it means that the include directories are only added to the target hello. And in this case, they're only added to the target goodbye. So you can imagine hello and goodbye could have different dependencies, and they could have different needs of -i and -d stuff added to their command lines for compilation. So this is a bit more specific to what the need actually applies to, but it's still wordy. Like, we don't actually want to specify these things at all. What we want is just to specify dependency with target link libraries and have all of that compilation requirement magically determined. And that's what Modern CMake is, really. I can go one step further from this, and I can put 2 colons in there in the name of the library. And this is maximally Modern CMake at this point. The double colons indicate to CMake that this is a target name. I'll go into a little bit more depth about that later too. So when you're writing Modern CMake, it'll look mostly like this in wherever you define your executables in your libraries. You'll have add executable or add library. You'll specify some sources, and then you'll use target link libraries to specify what the dependencies are. And all of the dependencies will have some double colons in them. So what we moved away from is the include directories command, which is not target specific. We want to move to a target-based build system definition, where most of what we're doing is just expressing dependencies between different targets. We want to have a single point of dependency specification. So remember that when I defined my executables, I didn't have to explicitly mention the dependency on the salutation includes and then also the salutation library as a link dependency. I only had to specify one thing, which was the link dependency. Everything else followed. And that's because the targets themselves provide that information to their dependers. All of the requirements needed to compile and link are built into the targets themselves. So how do we actually write lib salutation such that that works for those executables? And the way to do that is use the target include directories command and say that there's a public requirement to use this include directory. So in this case, you can imagine that salutation.h lives in the include subdirectory. And that's the directory that all dependers need to use. So target include directories. Anytime that you're using a command which starts with target, there's a good chance that you're doing the right thing and using Modern CMake. There's a question.
Instead of the whole current source directory, other braces, just doing a /include, isn't the dot resolved?
Right. So the remark is that I don't actually need to write this out because /include would be resolved to the current source directory anyway. I think that's true. I'm usually explicit about it, but that's also the case, yeah. Another question?
I like the dot version better because I think it's less wordy.
Okay, so the dot version may be preferred because it's less wordy. It's a good point. So there was a keyword there in my use of target include directories where I used public. I could also have used private and interface. I have to use one of those, and they each have a different meaning. And you might wonder what that meaning is. So to illustrate that, I have a my class here in my C++ code, and it inherits foo dependency, and it append includes foo dependency. Now, assuming my class is in my class.h, anyone append including my class.h will also have to be able to find foo dependency, the file. However, my class uses bar dependency internally in the C++ file, and the C++ file also includes bar dependency.h. Any dependency which uses my class.h doesn't need to be able to find bar dependency.h. So that's why bar is a private dependency of my class, and foo is a public dependency. And just to illustrate that with a diagram, you can see that the executable will need to be able to find foo.h, but it will not be required to find bar.h. So that's really the difference between public and private. I also mentioned interface, and that is relevant mostly just for header-only libraries because it means that a certain directory is needed for clients, but not for compiling myself. So interface might be a little bit more advanced. So just a summary table there as well to hammer that point home a little bit. It's something that trips people up a lot. What does public and private mean? It's my most upvoted answer on Stack Overflow, so I kind of think it must be relevant somehow to people. So we have a view of Modern CMake where you use target include directories. I also mentioned these keywords, but the thing is that you can use these keywords and the content multiple times in one target include directories call. So you can make it a little bit less wordy. So just to explore the include directories command a bit more now, what's so bad about it? So for one thing, we know that it affects multiple libraries at the same time, whether or not that's actually desired. Another thing is that order may or may not matter. So in this case, when reading this code, you might think, well, include directories comes first, so that's going to affect lib.a and lib.b. But what if it comes in the middle? Is it going to affect lib.b but not lib.a? Any votes, show of hands? Who thinks it's going to affect lib.a? 2 people, 3 people. It will affect lib.a, and that's because CMake way back was kind of aiming to be a bit more declarative, and all of the commands that were created back then affected everything in the directory. So in this case, sumdir will be available to lib.a, or rather this command on line 3 will affect the command on line 1. That's also true, of course, if you put it at the end. So it might make you might wonder where certain include directories are coming despite order that you see in your CMake code, but that's just how it works. It can get more confusing and complicated though, because now I'm still defining lib.a, but now I'm also adding subdirectory dir1. Then I call include directories, and then I have another library and another subdirectory. In this case, lib.a is still affected. Anything inside of dir1 is not affected, and anything inside of dir2 is affected. So again, it's a bit wild. But you might see even older CMake code which uses the subdirs command. And if you see that, the content of that is affected by this include directories command. So I just want to illustrate to you that if you're using commands like this that are very old, you're going to get the archaic behavior of CMake, which is not very obvious all of the time. Another issue with the include directories command is that it's not transitive. We saw some transitivity earlier. That was where an executable depends on a library, which has public and private dependencies. So the includes are sort of propagated up through the public edges. Code which does not use the target include directories command but uses the include directories command instead tends to have these kind of variables that it defines. So we're saying that the app includes are a combination of the lib1, lib2, and lib3 includes, and then somewhere down here we invoke include directories with that. So part of the problem with that is there could be a great distance between line 8 and line 1. They could be in different subdirectories, entirely different parts of your build system. Another problem is this list then has to be maintained. It might be maintained badly. There might be typos. Libraries might be removed or added. And you could have all kinds of problems in your build system. And again, it's also very wordy. So in this case, we would be creating a variable for includes and for libraries and affecting all of the subdirectories and the app itself. So that gets unwieldy, and that was the first motivation for creating Modern CMake way back in 2011. So that was the include directories command we were talking about. There's another command called add definitions, which has all of the same drawbacks. It works in almost the exact same way. Here's a call to it here where we're defining use internal SIMD and use multi-threading, which you might have in your build system. But an alternative to that, which we have now in Modern CMake, is target compile definitions. And that works the exact same way as target include directories. They have the same design. They have the same keywords, public and private and interface. And they work the same way. So if you're looking at code like this, which is using target commands, you're looking at Modern CMake. So there are other commands as well which use target prefixes in their name. These two we've looked at already. Then there's target compile options for adding FPIC or warning flags or any other compile command line option. Target link libraries, target link options, and target sources. So you can define a target and then later you can add sources to it. The only odd one out in this list is target link options, because that was created in the last year. All of the other ones have been around for years, so you can already use them. Even though this was only created in the last year, it doesn't, well, there's a good workaround if you want to use it, but can't, because all you have to do is pass the same arguments to target link libraries. Target link libraries is a command which does a lot of things, maybe too many things, which is why target link options was created. But it is a workaround for the lack of that command if you're using an even older CMake. Yeah?
Is there a simple way to enforce using the modern syntax? Issuing warnings or on deprecated commands like include directories, stuff like that?
Well, if you tell anyone I told you this, I will deny all knowledge. But you can actually redefine commands that are built into CMake. You can override them. So you could override it with like a fatal error or something if you wanted. But again, I didn't say that. But yeah, you shouldn't do that really. There's a lot of reasons that you shouldn't, but that's just the answer to your question. All right. So just building up this list of guidelines that I'm trying to give you. There's going to be about 4 at the end. So we've got the second one now, write target-centric code. And mostly that just means use commands which have a target prefix. Oh, another thing which might excite you is there's a new command just went into CMake last week called target precompile headers. So I believe it was someone from the Qt company that did that. implemented that for the purposes of Qt itself, because they want to be able to define precompiled headers in their build system easily. So that was, yeah, that was committed just last week. So that's the very latest. And of course, it works the same way. It still has public, private, and interface keywords. The design is being, used consistently from the past to the future. So, when I talked about the lack of transitivity, I talked about the resulting need for creating variables, which people do in non-modern CMake. That has a few downsides. You don't actually want to rely on variables for things. So here I have a new build system again. I'm defining main sources, which contains just main.cpp. And then I pass that into add executable to create app. I have an app includes variable, app defines, app libraries. And they are not defined in the same file as this. So they're defined elsewhere. So the problem is, maybe because of different ordering of subdirectories or something, or somebody commented something out, CMake might see this. CMake might see no content at all. The variable might be treated as not defined or empty. And that's not an error from CMake point of view. Variables can be empty, and that's not a problem. But it is a problem for you because maybe it wasn't intended. So what you should do is try to avoid the use of variables. Don't create some kind of sources variable and populate it, with different conditions and whatnot, and then at the end call add executable. Just try to list all of the sources you can in add executable directly, and then anything else that you might conditionally want to add, such as Windows-specific sources, you can add them in conditions after. I'll be showing some slides about that in a moment. Here as well, I'm listing the libraries explicitly instead of using a variable. There's 2 points about this.
Is it possible to set a policy to enforce that the variable exists?
Is it possible to use a policy to enforce that a variable exists? No, because it is a normal state.
Yes, but it makes a lot of trouble in the code.
It makes trouble. It's also relied upon. It's like, it's like trying to say that C++ shouldn't be dependent on, or, based on C anymore. There's some trouble that arises from that, but it's really not worth it to fix it.
Yes, but it's very difficult to find those errors.
It's difficult to find those errors. I think maybe the solution is migrate CMake away from the CMake language. It's a bigger task, but in practice, there's no way to do what you're asking, I'm afraid.
You can add checks for it in your CMake file and make your build fail if the variable is fuzzy.
Is there a comment over there as well? No. Okay. So yeah, there are issues with variables. So you should try to reduce the use of useless variables and just list things exactly where they should be. That's because variables are fragile. They leak to other contexts, so they leak into all of your subdirectories code, which you may or may not want. They don't have the same scope as your targets. So again, they're not expressing the scope of dependencies. And they're not checked for correctness or content. So I think that's what your remark was about, that these issues should mean that the behavior of variables should be changed, but there's too much CMake code relying on the existing behavior. So that's our third guideline, avoid unnecessary variables. Now, onto generator expressions. This is a topic which you might not encounter it in your first month using Modern CMake, but you will most likely encounter it after that. So I mentioned before that we want to avoid using variables. So this is what non-modern CMake might look like. You might have a variable called main sources, and you have a condition, and you append to that list, and at the very end, you create your executable. The way to not use variables in that case is to put everything after the add executable line instead of before, and use the target sources command. So now I'm not using any variables, so that's already one step in the right direction. Another step in the right direction is I could actually just list those things in the add executable call by using this funny syntax. So this is a generator expression. Just to break it down a little bit, I'm checking the win32 variable. I'm converting that to a bool so that it's 0 or 1. And if it's true, if win32 is true, then we use helper win.cpp. If not, win32 is true, then we use helper posix.cpp. Now this sort of stuff you might not want in the main bulk of your build system. You don't want to be writing it throughout all of your build system code. But what you can do is define some helper target for yourself, which abstracts that away a little bit. And then most of your code will still just be add executable and target link libraries. And that's always your goal with Modern CMake. You really only want most of your CMake code to be using 3 commands, either add executable or add library and target link libraries. Mostly that's what you want. Yeah?
What exactly does helpers and platform refer to? Platform is target, right? And helpers is?
Sorry, helpers : platform is a target name.
Okay, so that's one single name?
That's one single name, yeah. I'll talk more about this double colon in a minute, but it just indicates to CMake that this is a target name. It comes down to the target link libraries command and how it works in terms of legacy behavior. Yeah, but what to take out of this slide is that you can create abstraction targets and then simplify most of your CMake code just by relying on the target link libraries command. Yeah, another comment.
So now you have a target, a library consisting of actually the CPP files. So when I compile main, I will also compile the correct. It's not a compiled library. It's just a
correct.
A
So
collection of.
Yeah. So the remark is that this is a library of sources. So this isn't a compiled library because I'm using the target sources command with interface. It means we're not going to build anything ourselves, but anything that depends on this will use these sources. So typically something like this would be in the same file as this maybe, but it kind of simplifies what hello.executable does, or looks like. You can create a compiled library for that, but I'm kind of trying to illustrate different ways of specifying sources, which are conditional. Yeah.
That can have implications with the linker, right? Like, it's not exactly the same as having a library that is compiled and then linked.
So the remark is that this isn't the same as having a library containing one of these sources and then linked, and that's true, but it is the same as this code and this code. I'm just trying to illustrate that there's other ways of conditionally making a source file part of a target. Yeah. Okay. So this can actually have a correctness impact on your code as well. You might see this kind of code in non-modern CMake, where you're checking the CMake build type and checking if it's equal to debug or equal to release. This is non-portable because it won't work with Visual Studio. If you've ever used Visual Studio, you know that you launch it, and when you want to build, you can select to build either debug or release. And that's way after CMake is run. So what you need to do is tell CMake that if it's generating for debug mode, use helper debug, and if it's not generating for debug mode, use helper release. So CMake doesn't know if it's using Visual Studio whether you're going to click the debug button or the release button. So you have to kind of tell it what to do in each case. So it actually generates different Visual Studio project files for each mode. And that's how you communicate that. So those generator expressions, they get evaluated after the last line of your main CMake list.txt file at the top of your repository or anything like. CMake will process your CMake list.txt. We call that the configure stage. Then it'll compute various things, such as which target depends on which other targets and what order do I have to build things in order to be able to link. And then it'll actually generate the build files. And somewhere in between is where it processes those generator expressions. And that's helpful because the entire configuration step has been done already. So I'll tell you a little bit more about that in a few slides. So just to summarize the basics of generator expressions, 1, colon, and some content will result in the content itself. 0, colon, the content will result in nothing at all, empty. Config debug will result in 1 if it's generating for debug mode, and config debug will result in 0 if it's not generating for debug mode. So by nesting this one inside of a larger generator expression, we get this. And you can see how it would collapse and sort of result in the content or not the content based on basically these two simple rules and the fact that this generator expression evaluates to either 1 or 0. The bool generator expression will have some truthiness conversion, so it's able to process an empty string, for example. If I just put win32, which might just be empty, into a generator expression, it would not be a valid expression. So valid expressions have to be either 1 or 0. So if I use bool, I convert empty into 0, and that's why this kind of code can work. A lot of CMake commands have support for these generator expressions, but not every CMake command. Mostly that's because the commands are not relevant to generation. But hopefully all of the needs that you have regarding use of generator expressions are already there in your CMake version. All of the target commands can use them. The file generate command can use it too. That's something you would use instead of using file write if you want to have different content for debug mode and release mode. That's how you would have a portable build system to Visual Studio, etc. So most of the commands where it's relevant, it's possible to use generator expressions. So just another example of where that can be relevant. In this little snippet of CMake, I'm trying to get the property build with threads on the target hello. I'm trying to get the property called with threads on the target hello, and I put that into the variable build with threads. And I use that to try to add a compile definition use thread. So that's used with an if and def in my CMake code. And then later I set the property to on. So the problem is I've set the property to on after trying to read it. And that's because CMake processes this file from top to bottom. So the alternative way to do it is to use generator expressions, of course. We're saying if the with threads property is true on the target, specify the use threads in target compile definitions. So I appreciate that there's a lot to unpack in that single line, but you do get used to it, and it's quite powerful once you do. And now, even though I set the property to on afterward, it doesn't matter because setting the property to on happens in this stage, the configure stage, and testing it happens in the compute stage. So that means that I can't have bugs relating to ordering of commands inside of my CMake code. And this happens more than you think because you might have add subdirectory calls which change target properties and later they get read, and it might not be obvious what order things happen in. So, use generate time conditions correctly. So probably the last thing I'm going to have time to talk about is the target link libraries command. I mentioned before these double colons in target names, and I illustrated that this is what Modern CMake looks like when you're using all Modern CMake. All of your dependency libraries will have double colons in them. So the reason for that is the target link libraries command itself. It's very old and it has legacy behavior. For any item that you give it, CMake goes through a list of things that that item might be. It'll see if that item is actually a CMake target name, so a library like libsalutation. If it's not a CMake target name, it'll test whether it's a library name on disk, such as libsalutation.so. If that's not true, it'll see if it's /opt/libsalutation.so. It'll check if it's a path. And if that's not true, it'll treat it as a linker flag and simply add it to your link line. So that's why you can use target link libraries with link options, such as no undefined. But it also means that if I make a typo when trying to specify a CMake target name, it'll just be added as a linker flag. So if I have libsalute and that's it, and I forget to write the rest of the word, that'll just be added to my link line, and I won't have a dependency on that CMake target. So so this using an item with target link libraries has a bunch of impacts on your build system. It causes a link to be made on your link line. It determines build orders so that things are built before they're linked. It consumes usage requirements such as your -i and your -d on your compile command line and your link options. And it determines compatibility, which I won't get into now. But basically, you want to try to specify CMake targets where possible instead of library files or library paths. So I mentioned that if you do make a typo, CMake checks what it could be, if it's a target name, etc., and otherwise just adds it to your link line. And you don't want that, so that's why mostly you want to define targets with double colons in them. That indicates to CMake that either this is a CMake target name or it's an error. So I'm bypassing all of the other fallback logic that CMake cascades through because it always succeeds, right? It always gets to a success state of just add it to the link line, even though it's a typo. So if I have targets which have double colons in their name, CMake knows that it must be a target name. And if it can't find a target of that name, it gives you an error. So that's why you get Qt5 : core. That's why you get boost : thread, etc. And you can do that for your own libraries as well. So there's a number of target types in CMake. The top three are the ones that you'll use most often. That's executables, shared and static libraries. Object libraries are quite similar to static libraries, but they just don't create an archive. So it's just a bunch of object files. Interface libraries are used for header-only libraries, such as boost MPL. And alias libraries are just a way to give another name to an existing library. So for example, I created the libsalutation library, and I would create an alias called libs : salutation in order for all of the rest of my build system to be using target names with 2 colons in them.
Question.
Yeah.
Can I use : in the original libs salutation, or does that violate some file naming?
You can, yeah. Sorry, can you ask that question again?
do I need the alias? Do I need to first specify, let's
Oh.
say, lib salutation as a single word to have a
Yeah.
of a normal file name?
Okay.
And use the alias to give it the colon colon, or can I just go directly to the colon colon?
So the remark is, if I would just create lib salutation with the colon colon already, I wouldn't need the alias.
That's fine.
But that is not fine, unfortunately. Yeah. So when you create an actual build target that you're building in your build system, like a shared or static library that you build, as opposed to one that you import, it can't have the double colon in it. That's the convention that we came up with. So yeah, unfortunately, you do need the alias for that. I kind of like the idea of making that easier in the future, but it's the case now. So I have a few minutes to talk about dependencies. When you're using external dependencies, you want it to be basically this simple. You do find package, and you use target link libraries with a target name which contains 2 colons. Some older packages that you might use might say, well, first you call find package, then you call include directories with foo includes, etc. But this is what you're aiming for in terms of simplicity and lack of redundant commands. You simply find package and then you target link libraries. Because this works transitively, in this example I'm calling find package for Qt5 widgets. I have some local library in my build system, and Qt5 widgets is a public dependency of the local library. I also have hello, and that depends only on the local library, but it actually gets the include directories and everything from Qt5 widgets transitively. That's because local lib uses Qt5 widgets publicly. So it communicates that through the public edges all the way up. And as I mentioned, the legacy pattern of doing this kind of thing is very wordy. So what you would have to do with Qt4 way back in 2010, you would do something like this. You would call find package, and then you would use add definitions to add all of the -d definitions. Then you would use include directories to add all of the include directories. Then you would do some messing with your CXX flags. Then you would have target link libraries with some variables, and then you would set those variables as dependencies of the next stuff in your build system. So very wordy, lots of stuff to go wrong, lots of potential for typos. You don't want to do any of it. So the general wrong way would be you call find package, and that provides some variables like foo include dirs, foo compile definitions. You'll still find a lot of packages which only provide those kind of things instead of providing targets. So the aim is that a package that you use provides a target with a double colon in the name. And of course, if I have this correctly written, but I comment out the find package or I forget to write it in the first place, CMake will issue an error because it knows that this is a target name and it can't find it. So that's useful to you. Another thing to note is that foo core is what we call an imported library. And you can note that is similar to the syntax that you would use for alias libraries. So again, just the double colons. And I think that's my last guideline that I have for you, which is use imported targets provided by your dependencies. I think the find package scripts that are provided by CMake, some of them provide imported targets like this, but they also provide variables. So in that case, you should always prefer to use the imported target in your code. I don't think I have, anything else. So the wiki has a lot of outdated information, so I would recommend avoiding that. Do use the documentation. I don't know, people Google things about CMake and they find example code on Stack Overflow and on GitHub, but some of the answers are in the CMake documentation. The CMake mailing list also has good activity, and Stack Overflow does too. So the people answering questions on Stack Overflow do know Modern CMake and they do advocate for it, which I'm quite happy about. If you do look at the CMake documentation, start here with the CMake build system. That's like long form prose about how to define your build system, similar to this presentation. Then you would look at CMake packages. That is some documentation about how to create your own package files for your libraries. So yeah, just thanks to some of the CMake contributors, in particular Brad and Ben and Robert. And Reddit also gave me a lot of feedback for the content of this talk too. So yeah, there's a question.
Yeah, just a simple example from earlier. You have a lib salutation,
Mm-hmm.
and you have the executable hello
Mm-hmm.
into that. So what's the simplest way to get hello to link to libs : salutation? Do you just need to add the alias statement? Or is that it?
Yes. So the question is, maybe I'll go back to it. Yeah, all right. So the question is, if I want to make this work, how do I do it? And so you would need to use target include directories, but you would also need to create an alias. Yeah, that's the easiest way.
Right.
So I don't have that on this slide, but
Yeah, okay, so that's a new statement with add library and then libs : salutation, alias lib salutation.
exactly.
Okay.
Yeah, yeah. So yeah, maybe I should have that on the slide.
Do you have some comments about people using project name in nested way? Like if you have like several libraries in the project, and you use a new project name for each of them to get like so you can match the name, concatenate the name.
I don't have any guidance to give about that. So the question is about.
Correct?
Hmm?
Is it correct use or?
I'm not sure why people use more than one use of the project command. I'm not sure if you mean using project inside of
because You have
subdirectories.
that in the first, you get that name plus the other name to the library, and so you can like the libraries are getting some similar name. Just the last part is changed.
Okay. Yeah. So the remark is just about creating a naming convention. I don't have any specific guidance about that. Hi.
Yeah, sometimes it's about you have a library you depend on, but that is a open source library, whatever, that is not using CMake at all to build. And then you want to express your dependency on that, and that is makefile or autotools or scons or whatever other build system. And I found that like difficult, and usually I fall back to the old style CMake. Is any modern way of doing express that dependency?
So the remark is about using dependencies which don't use CMake themselves. They use some other build system. You would use the external project CMake module for that. And beyond that, you can create your own targets with double colons in their name to make it simple for the rest of your build system. So you mentioned that you fall back to old CMake way, which I guess is variables, etc. what you would do is just take those variables and define imported targets with those. So you would define an imported target yourself called boost thread, say, or boost system. And you would define what the location of the binary is, boost system.a, and you would define the include directories for that as well. And then after that, everything else works exactly like in the presentation. Yeah. And for examples of that, you can look into the into your CMake distribution itself. If you look in find png.cmake or so, that creates an imported target after creating the variables, and it just uses those variables. Yeah.
So, sometimes you want to have like a global optimization level, but in this specific library down there, I need to turn it off or something. And then you have a conflict about, you don't want global variables, but you also would like to have a default that you could sunset at the top level.
So how do you have a default global warning level, for example, and be able to reduce that in some specific target? You can do some messing with target properties, like I showed in the slides, and then at generate time have some generator expression specifying which one to use. But yeah, that gets to advanced topics then as well. Yeah. I think we have time for one more question. Yeah.
Can you point to some repos during Modern CMake?
Repos.
To look into.
Um,
You know what?
well, my own. Let's see. This is a Qt-based text processing library that I have and that I maintain for now. It's just got 2 libraries inside of it, so it's using a lot of modern CMake techniques. There's a bad example. But yeah, so using target compile features, yeah, it's actually doing a lot of wrong things. But it's using Qt 5::QML, so that's good. But yeah, maybe look at the KDE libraries as well. They're using Modern CMake and Qt as well, so could be a good one to look at. Okay, thanks for coming.